committee.
Oh, sorry. It seems like Dr. Porter was stuck in the waiting room.
Was she?
That's odd.
There we go. That explains.
Let's
There
see.
we go. There's Bruce.
Can I add someone as a? Let's see. Okay, I'm adding some people as co-hosts so that in case anyone sees someone in the meeting room, please go ahead and admit them.
Got it. Hello, everyone.
Hi, Professor.
Hey, Krishna. How you doing?
Great. So now we're just waiting on Professor Mikulánen.
Okay.
We should be good to go.
It looks like you have some support staff here. Good to see you.
Yeah.
Scott, good to see you.
Yeah, let me just add everyone as co-hosts. Yeah, I didn't realize you were stuck in the waiting room for a minute there, so I'm just...
Turns out I don't have the UT Zoom feature on my... I mean, Zoom all day long, but I don't have the UT.
I had initially, I didn't realize there was a setting to make it so that anybody with a Zoom account could join. So initially it was only, oh, here we go, he's here. Okay. I guess I'll start then in a minute.
Sounds good.
But yeah, Tyler should also be able to come now. But I probably won't wait for him, seeing as he's familiar with the introductory material anyway.
All right.
Okay, let's see. All right, then shall I get started?
Sure.
So, hi everyone, thanks for coming. So this is my thesis presentation on integrating hyperparameter optimization into a, oh, here we go, sorry, Tyler's also here now. Okay. Into a neuroevolutionary pipeline. So I'll start by just sort of explaining some background terminology, and then I can get to the actual sort of motivation and main idea of my thesis. So first of all, what is automated machine learning, or AutoML as frequently described? The basic problem of supervised learning is you have a data set with labeled training data, and you want to train some kind of model on this data set so that you can draw predictions given future unlabeled data. And this is a very, very black box sort of a problem. You don't generally care what kind of model you're training. You just want to train a model. And usually, the problem of selecting a model architecture and trying out different things is generally left to a human being, not to a computer. Usually a computer trains the model once you've picked one. And sometimes you call this meta process grad student descent. So the idea of automated machine learning is to do some kind of search over different kinds of models and pick the best one for a given problem. Now, what's hyperparameter optimization? So when training some kind of model, usually you have various aspects of the training process that you can tweak. And these are just generally called hyperparameters. So in the context of neural networks, the most well-known ones are batch size, the learning rate, the optimizer used for the learning rate, and so on. And some of these will show up later. So if anyone's not familiar, batch size is basically how many training examples do you look at a time when updating your model. And the learning rate is how big is your step size. So given some new piece of information, do you change your model a lot or just a little bit? And generally, you want to decrease that over time. So now that we have some definitions, here's the main question of the thesis. How do you integrate hyperparameter optimization into an automated machine learning pipeline in general, and in the specific context of a neuroevolutionary pipeline, ideally? So we use Darwin, which is an enterprise automated machine learning platform by Spark Cognition. So the first question is it even worth the effort, right? If you integrate hyperparameter optimization, does it actually help that much, given that it may impose additional resources constraints? And does that usefulness, if there is any usefulness, does it depend on what kind of data set you have? So can we somehow characterize the data sets that do benefit? And this question of characterizing data sets ends up being more interesting than you might expect. So first of all, automated machine learning is a very broad area. So what do papers tend to look like? There's sort of three kinds of papers you tend to see, or three kinds of platforms you tend to see. It's quite common, especially in academia, to take a single data set, like CIFAR 10 or a language data set, it's a kind of established problem, and then build a really nice search space for models for that one data set, usually for neural networks. And so there's a lot of such papers. Real et al. 2019, they use evolutionary algorithms to search. Then there's like a NASNet search space. There's a lot of search spaces basically for these very specific data sets. There's also some papers where you have many data sets, but you also don't train necessarily very sophisticated models on them, like neural networks. Instead, you may see cheaper models like support vector machines, gradient boosted decision trees, and so on. For them, because they're not doing backpropagation to train neural networks, they sort of treat everything like a hyperparameter, including the choice of model. And there are papers that do that. And then finally, you have sort of the biggest and most interesting general problem, which is what if you have a lot of data sets, but you're also trying to train powerful neural networks on them? And a lot of enterprise platforms do this. So you have Darwin, of course. Offerings by Google and Microsoft tend to come under here. And this is sort of the question we're tackling, is what do you do with hyperparameters in this context? Because hyperparameters are not, while you can think of them as sort of analogous to choosing a model architecture, in practice, when you're searching over different architectures, you're not also searching hyperparameters at the same time. They're sort of orthogonal components of picking the best model. So now we're just zooming in on neural networks. We're not talking about other kinds of models. And if you're just searching neural networks, you generally call that problem neural architecture search, or NAS. And there are a lot of different kinds of approaches. So one very notable early paper by Zof et al. Was in training a recurrent network using reinforcement learning to take in a data set and spit out descriptions of models. So it would literally describe neural networks, which you would then train. There's also various approaches focused on efficiency, like ENAS or parameter sharing, where you train like a mega network. There's network morphisms. There's a lot of approaches. But the one we're focusing on is one of the earliest ideas, which is evolutionary algorithms. So you start off with some simple networks and you evolve them over time by adding to them or changing their architecture, and you basically see if you can get better performance over time. And this is the system used by Darwin, as the name might suggest. So how do you actually optimize hyperparameters? There's a couple different ideas. One is just try evolving the hyperparameters over time. The approach we're going to use is a little different. Instead, we're going to try optimizing them after we've actually run the AutoML pipeline. So we have a sort of sane default set of hyperparameters when we run the automated machine learning pipeline. And then when we're done, we get some models that perform reasonably well. Then we try running a tune step, where we retrain the models using a couple different sets of hyperparameters, and we see if we can improve the performance in any way. And in the process, we're sort of assuming that the best model architecture is not dependent on the best set of hyperparameters and vice versa, which is a bit of a dubious assumption, but we're just going to run with that for the moment. Random search is a very effective method for hyperparameter search, as it would turn out, but we're also going to try another algorithm called hyperband, which has been gaining a lot of traction. So let's talk about hyperband then. Hyperband is a proposed solution to a very famous problem in AI called the many-armed bandit problem. The idea of the many-armed bandit problem is as follows. You have an infinite number of slot machines, and you can pull a lever at each of the slot machines. When you pull a lever, you sort of expend one resource, so you have a limited time budget, and at the same time, you gain a reward from a hidden random probability distribution. it's very important that you don't know what the distribution is, because you have to expend resources to figure out which slot machines are going to give you the best bang for your buck. But at the same time, if you waste too much time in exploration, you don't have enough resources for exploitation. You can't then figure out which machines to pull the lever at the most. This is surprisingly analogous to hyperparameter search, where you can think of each slot machine as a different point in your configuration space, a different set of hyperparameters to try training with. And then pulling a lever is like allocating resources to training that model. This is pretty cool because you have now a notion of partially training a model, of only pulling the lever a few times. Let's say only training for a few epochs, rather than, let's say, a more Bayesian approach, where, if you see Bayesian approaches, they tend to treat everything like a black box. And they think of training a model as evaluating a function that they don't know the answer to. So they will always train for the same number of epochs. Although, of course, there are hybrid approaches and more advanced methods that also try to incorporate ideas from bandit algorithms. One of the most notable algorithms for the many-armed bandit problem is called successive halving, which is the basis for hyperband. And the way successive halving works is very straightforward. You pull all of the levers one time, or at the very least, you take n samples, n random samples, and then you pull each one a certain number of times. Let's call that R. Then you take the half that do better, that have given you a better reward so far, and you keep them, and you discard the other half. For that half, you now train them for 2 times R epochs, or you allocate them 2 times R resources. And then again, you discard half. And now you do 4 times R, and then discard half, and so on and so forth. So an exponentially small subset of your configuration space is given exponentially many resources. And this works out very well, both in theory and in practice. But there is a sort of subtle problem with it, which hyperband tries to address. Namely, there is this thing called the n versus b over n problem. It's as follows. It's not obvious a priori, it's not obvious a priori if you should take a lot of points in your configuration space and maybe not give them that many resources on average per point, or if you should instead take just a few points in your configuration space and give them a lot of resources, given, assuming some fixed budget B. So if you try to take as many points as possible, you end up with what is just regular successive halving. But if you're willing to stop successive halving after a certain number of iterations, like instead of having all the way down to just one model, if you just have down to maybe a quarter of the models or an eighth of the models, then you have sort of intermediate runs of successive halving where you've not allocated as many resources, but you have more models. You've taken more points in your configuration space. And if you take this to the logical extreme, you just run one iteration of successive halving, meaning you don't have anything. And now you just have random search, where you allocate an equal number of resources to all models. Hyperband it's not really intended to run all the way through to random search. It is an anytime algorithm. So you can see here, you calculate your budget, you create a priority queue of the best samples in your configuration space, you run successive halving iteratively, and every time you just check to see if you've hit a time limit. So why is it that we like hyperband so much? There's a couple of reasons. First of all, as I just mentioned, it's an anytime algorithm, which works very well with neuroevolution in general, because neuroevolution is also an anytime algorithm. You can stop after any generation. And it's also generally very good for practical use, because generally you want the user to provide some kind of time limit. And it's not easy to predict in advance how much you'll be able to run a certain algorithm, or how long something will take to run, given varying sizes of models and so on. So that's one nice aspect. Another nice aspect is that it doesn't ask you to reason about the shape of your sampling distribution. Bayesian approaches will often sort of, treat categorical variables differently from like continuous variables and so on. You can sample however you want. In fact, you could even condition your sampling space on the kind of model architecture or on the kind of data set that you're using. You have a lot of flexibility in that regard. So that's great. We found early stopping, which I had mentioned earlier, that you can allocate just a few resources to a model and then quit quickly if it's not doing well. we found this to be very useful in practice. So a lot of data sets, as we'll talk about later, do extremely poorly with small batch sizes. And it would be very obvious in advance that they were not going to do very well, and being able to stop them quickly is quite useful. And finally, it's just easy to implement. I mean, the entire thing fit on 2 slides. Compared to some of the more sophisticated algorithms out there, we could be confident that we done it quickly and correctly. All right, so that was a lot of background, but now we can finally talk about how hyperparameter optimization does in any revolutionary pipeline. Just kidding. First, we have to talk about how we actually characterize our data sets, because we're trying to figure out what kinds of data sets might benefit from hyperparameter optimization. And in the process, we also sort of want to know what kinds of data sets we're hoping benefit. In other words, which data sets really have room for improvement already. Because if we're already doing extremely well, we don't necessarily care that much how they will do in the future. So how do we summarize data sets? How do we, because data sets, I mean, there are a lot of data. You need to pull out just a few numbers to figure out, to explain how the data set is shaped. And turns out people have already done this work for us. These are called data set meta features, and they come from the meta learning literature. So meta learning is, you can think of it sort of as a generalization of automated machine learning. You're still sort of trying to solve the same general problem, which is given some arbitrary data set, build a model for it, and do as well as possible. But meta learning goes a step further. It asks, can we learn from experience? We've already seen a bunch of data sets. We've already built models for all these data sets. Can we, knowing what has worked and what hasn't worked in the past, can we build more effective models in the future? And this is sort of what humans do, if you think about it. Humans will look at data sets with the time series components and they'll go, oh, I guess this could use an LSTM or something. So meta learning is sort of trying to get a computer to do that as well. And of course, when you're trying to solve this problem, it is very useful to compute statistics about the data sets you've already seen. And they can be very simple statistics, like how many features are there, or how many classes are there, or what's the ratio of features to classes, and so on. So this is the only math you're going to see in this entire presentation. We're taking our conventions from a paper by Adriano Rivoli et al. Called Characterizing Classification Datasets, a study of meta features for meta learning. It's basically a very nice, comprehensive study of different kinds of dataset meta features, and they also created a great Python library to help us extract them. So we model a dataset as a sequence of n labeled points, well, I guess a set of n labeled points, but in practice it doesn't matter. I guess sequence does matter for recurrent problems, now that I think about it. Our dataset pool is just a set of these datasets, and a meta feature is a function from our dataset to n tuples. This is where Rivoli et al. Sort of breaks off from most other papers. They go further, and they break up a meta feature into 2 components. What they call a characterization measure, which is what you normally think of when someone says meta feature, and a summarization function, which, if you've generated a lot of data with a given meta feature and you want to summarize it somehow, you can take quartiles, mean, median, max. You can take standard deviation, skewness and kurtosis, which are more advanced statistical measures. Skewness essentially measures how asymmetric is this distribution. Kurtosis is, if there is a peak, how sharp is the peak. These sorts of metrics are sort of applied after you've taken the initial characterization measure, and you put them together, you get a meta feature. HM and HS are just hyperparameters. We set these to same defaults. And there are a lot of different kinds of these meta features. In fact, these are just the most well-known 5, and we pick these for our purposes. But there are even more than this. Rivoli et al. Describes concept-based meta features and various other kinds as well. But these show up in quite a few papers. So general meta features tend to be easy to calculate, easy to think about. Some of these we actually already have in Darwin, so we don't have to go out of our way to find them. For example, Darwin tracks whether a data set is a regression problem or a classification problem, whether it has a recurrent component to it, and therefore can benefit from time series models, or whether we should just use a more normal model instead. And then, of course, ideas like width and height. So width meaning how many columns do we have, how many features. Height is how many data points are we given. Statistical measures are, like I mentioned earlier, skew and kurtosis. To be clear here, there's a subtle distinction. These are metrics that we apply directly to the data. So we take the data set and we compute these measures directly on the data. Whereas earlier when I was talking about these, this is after you've applied a meta feature. Then you may want to summarize the meta feature using those the same skewness and kurtosis. So subtle difference there. Information theory is a rich source of meta features, as you might imagine. So information entropy, how much information is there in a given column? If one of your features is just 1, 1, 1, 1, 1 all the way down, I mean, there's no entropy there. You shouldn't really care about it. Mutual information, likewise, if two features are virtually copies of each other, then you care about that. So these are very useful. Landmarking and model-based meta features are similar in their purpose. Basically, the idea is you want to estimate how difficult your data set, and ideally, in what ways is it difficult? So landmarking meta features, generally what you do is you take a simple, well-understood model with well-understood biases. For example, naive Bayes or an SVN, and you train it on your data set and you see how well it does, and you just take the score. And if it does really well, it's probably not a very hard data set. And if you know which kinds of models do well, then you get an idea of in what way is it easy. Model-based methods are kind of similar. You train some decision trees on your data set, but instead of taking the score of the trees, you look at what the trees are shaped like. So you look at how imbalanced are they, how many leaves do they have, how many branches. And intuitively, a more complicated tree can be indicative of a more difficult data set or a more chaotic data set, and so on. So both of these are meant to give you ideas of how difficult they are. And we're going to hope that later they will give us the information we're looking for as a result. So what about the data that we're using, right? We source data sets from a lot of places. There's online challenge data sets, various repositories. Spark Cognition has data sets from their clients as well. And there's also data sets that are generated internally as synthetic data sets so that we can test out certain types of models. You'll notice that there are a lot of time series problems. So this is a total of 17 time series problems to 21 non-time series. Almost half of the data sets we're using are time series. But there aren't many language or vision data sets. So, I mean, of course, language data sets can be thought of as time series in the sense of, if you encode everything using word embeddings, then it's essentially a time series problem. But the data isn't actually coming from a language source. So we don't really have any of those. And vision models are not really supported in the system we're using. So you also might notice that there are quite a few more classification data sets than regression problems. Here are some examples. So we have quite a variety of data sets. So this is sort of an indicator of that. These two, so tree imbalance and canonical correlation. So this is a model-based metric which is intended to estimate data set hardness. Likewise for canonical correlation, this is a statistical measure of correlations between features and labels. We'll talk more about these later. I picked out these because they tend to show up later in my paper and also this presentation. If you'd like more information about them, you can always check out the paper. And then this is a information theory measure, which will also show up later. But yeah, the main idea is we have quite a few different sorts of data sets that we'll be playing around with. And now we can finally try to actually answer the question that we came to in the beginning, which is, well, there's a couple of these questions. So let's break them down further. First of all, what kinds of data sets actually have room for improvement? And can we predict those data sets using meta features? So now, once we have an idea of that, we'll ask, does hyperparameter optimization actually help when we implement it? Does hyperband versus random search make a difference? What kinds of data sets does it tend to help for? And can we predict them, again, using meta features? And if it doesn't help, we also want to know what are some sane defaults, because if we're not implementing hyperparameter optimization, we might as well pick some good numbers to use internally. So let's start by figuring, just a quick bit of setup. So we found 20 minutes to be a very reasonable default for running our main automated machine learning algorithm. It was long enough for the LSTMs and TCNs that we use. LSTMs being, they're both time series models. It was long enough for them to start outperforming the simpler models on time series problems. And it was just generally basically a good baseline of the documentation. We then either kept it as a control group, or we continued training using various hyperparameters, either using random search or hyperband for 5 or 10 minutes. We did all training on a single machine, GTX 1080, and we didn't use anything other than neural networks. So Darwin does have support for boosted decision trees, random forests, and so on. We just stuck to neural networks for purposes of this testing. And finally, we tried doing all of our experiments twice, once with and once without learning rates in our search space. And this was for a secondary hypothesis that we're trying to test here, which is, do bandit-based algorithms actually do better or worse? The reasoning is as follows. If you have, imagine you are a bandit-based algorithm, and you have a bunch of different models with various learning rates. If they have a high learning rate, then you may end up seeing that they improve faster in the beginning, and therefore allocating more resources to them, even though later on, when training, maybe they don't stabilize to as good of a local minimum. And so maybe, the algorithm is tricked by the way the learning rates impact training. So just as a secondary hypothesis, we're going to try both with and without learning rates to see if that actually makes a difference. So first of all, what kinds of data sets are we actually worrying about here? Because most data sets, in practice, they're not that difficult. And you can see here we have, so at first it looks like our classification data sets are much easier. That is generally true, but in practice, we have a lot of synthetic data sets, which are generated right here. And Darwin is generally quite good at dealing with those. On the other hand, we have quite a few regression problems that are very, very difficult. And so we're hoping that these may see some kind of improvement when we start searching over our hyperparameters. We mentioned earlier that we were hoping that model-based and landmark-based methods could predict difficulty of data sets. And sure enough, they definitely show up here. So especially model-based methods, pretty much like all of these are taken from training a decision tree and then figuring out how well it does on our data set. There's a bit of there's a subtle error here. These correlations are flipped, so this is actually the best metric. But in any case, also notice canonical correlations of a statistical method. Sorry, let me take a step back. Canonical correlation analysis essentially works by taking linear combinations of your features and trying to maximize their correlation with your target labels. So if it does well, then you will find that there is a strong correlation, strong hidden correlation. And in principle, that would imply that the problem is easier. And in fact, that is exactly what we find. The problem is easier if there's a lot of correlation. But otherwise, yeah, model-based methods do very well. Landmark-based methods, other than this naive phase, they don't really show up that much, surprisingly. But overall, things are as expected so far. Now, what about hyperparameter optimization? Surprisingly, or maybe not surprisingly, it doesn't help that much in general. It helps in some data sets, as we'll see in a minute, but on the bulk of data sets, it does not actually make that much of an impact. Now, what's a little more surprising is that learning rates are very, very bad for performance. Rather, if we allow our hyperparameter search algorithms to try out different learning rates, they tend to do much more poorly, which may be a bit of a surprising fact, but consider that we are running on relatively strict time limits of 5 and 10 minutes respectively. It's not that crazy to imagine that if you pollute your search space with a lot of bad options, they won't have enough time. Even an algorithm as effective as hyperband, in principle, may not have enough time to cut out the poorly performing models and stick to the ones that do relatively well. So increasing your search space is not, necessarily a good substitute for actually understanding what kinds of parameters are actually worth searching over. Now, we did see some data sets do better with hyperparameter optimization. So there were, especially, there was one synthetic data set, which was a very difficult regression problem that did much better. But then there are also several other data sets. These generally tend to be regression problems. Most of these are time series, except for this Boston data set. They all have, they're all relatively large and difficult. So these are pretty much the kinds of data sets we were the most concerned about, and it is somewhat promising to see that they are doing better with our hyperparameter search. Now, are there any meta features that predict whether these data sets are susceptible to this kind of improvement? And surprisingly, we see a lot of information theory-based methods, which is not something I was expecting personally. Goodman-Kruskal tau is a metric that measures how strong the relationship is between two different variables. So the strength of relationships between attributes and between classes, those both show up very high. They both come quite high on our list of correlations. Mutual information, joint entropy. I mean, it's pretty surprising how many information theory-based methods show up. But at the same time, we can't just automatically assume that these are actually going to be good metrics, because we also see several things that are clearly nonsensical. For example, what would the harmonic mean, or the geometric mean, or the standard deviation of the geometric mean of our data? What could that possibly have to do with the efficacy of hyperparameter optimization? And in practice, when investigating these correlations and actually graphing them, we found that indeed, these tend to be overly influenced by a very small number of outliers, which makes these correlations quite clearly spurious. So here are some example graphs. You can draw your own conclusions, but it's quite clear that even if there is a correlation, these are some of our best. So here's attribute concentration, Goodman-Kruskal tau. Here's class concentration, and you can see that even if there is some kind of correlation, it's not at all clear or strong. And then here's an example. So this is the ratio of numerical features to categorical features, and you can see that there are two outliers, and here as well a few outliers, which have a very strong influence on the correlation coefficient. So, well, I mean, essentially what this one is saying is, if you have a lot of numeric features, it's probably going to benefit, which is kind of indirectly saying what I was already thinking, that regression problems tended to have, they tended to benefit more from this kind of a thing. But that, again, could just be a spurious correlation. So it's important to always go over the graphs and verify that you're not just looking at random noise and drawing your conclusions. So, all right, let's say that we're not going to use hyperparameter optimization. In that case, we do want, at the very least, to have sane defaults. And so what would those sane defaults look like is the natural next question to ask. This is a heat map of not the hyperparameters of the outputted models, but of the models that Hyperband specifically chose to continue training, which is why, like, even on the lower end, you're going to see relatively large numbers. But you will notice that pretty much across the board, bigger batch sizes do better. They are strongly preferred. And this is also something we found when testing earlier, that large batch sizes were extremely helpful for the more difficult data sets. Our conjecture at the moment is that these difficult data sets tend to have a very low signal to noise ratio. And if you have a large batch size, you can average out a lot of the noise and just focus on the signal. But smaller batch sizes tend to struggle with this. The usual argument for small batch sizes is that they can act as a regularizer. So you can avoid relatively small and shallow local minima and focus on larger, deeper ones. But I think it's pretty clear that larger batch sizes definitely win out here. As for optimizers, however, there isn't really a clear winner. Nothing that is outside of what could be considered a confidence interval. So in conclusion, the hardest problems are big, difficult regression problems with the time series component. If you want to estimate how difficult a data set is, model-based methods are far and away dominant, as well as canonical correlation analysis. If you compare it to having same default, hyperparameter optimization, even on a wide variety of data sets, as we've chosen, is not necessarily terribly helpful, especially given that it's going to cost you time if you're running it like this as a tuned step at the end. But bear in mind that we haven't used every kind of data set out there, and there could be more subtleties when dealing with, say, vision problems and the like. Information theory-based methods may work for predicting the usefulness of hyperparameter optimization, but more research is needed. And in terms of same defaults, bigger batch sizes are helpful. Optimizers, maybe not so much. And learning rates, stick to what works. Because if you pollute research space, you can end up wasting a lot of resources. So in terms of future work, one thing that we did try to do for this paper, but unfortunately couldn't get working in time due to certain technical issues, was actually evolving the hyperparameters over time alongside the model architectures. And there are papers that do this, for example, CodeNeat, which was published last year. Then, of course, generally, it's always fun to scale up. So adding more hyperparameters to the search space, like different learning rate schedulers, decay, dropouts, although we have tried dropout before, different methods of training learning rates like warm restarts and so on, different initialization methods like Xavier initialization. That would be interesting to see which of those tend to be more impactful and what kinds of models they tend to work for. Generally, just widening the pool of data sets. If we were to add vision or language problems, this could be a very different looking paper. And finally, that one odd looking link we found, link we found between information entropy and hyperparameter optimization efficacy, that may be worth further investigation before dismissing it outright. And that's basically it. Any questions?
Hi, thanks for the talk. It's pretty cool. So I wanted to first really quickly clarify, can you remind me, did you run these for like a fixed number of epochs or for a fixed time before you moved on to the next stage of multi-arm bandit?
Good question. So everything was based on an external time parameter. So essentially, both neuroevolution and then random search and hyperband have an iterative sort of structure to them. So you run like an iteration, and then you check to see what time is it, have I gone over the time limit? And if you have, then you stop. If you haven't, then you keep going.
All right, yeah, so my follow-up to that is, it seems like you identified that learning rate has some bias towards the performance of the models. Like the models with the higher learning rate will be chosen earlier, but then they could actually be, have worse performance at the very end of training. But I'm curious, I feel like that isn't just limited to learning rate. So if you look at batch size, just the fact that models with larger batch sizes tend to train faster, so they would have made it through more epochs by the wall clock time limit that you set. Alternatively, if you're looking at stuff like using larger hidden layers, those could potentially take longer to train, but could have better performance later on. And so even on an epoch level, those could take more epochs to achieve comparable performance. So I'm curious if you've thought about the implications of that the different hyperparameter values have on how quickly.
Yes, so that's a great question for sure. So one thing I sort of left out is that this was my internship work over the summer, right? And initially I was testing with a much smaller pool of data sets, so just the most difficult ones, the Beijing data sets, certain UCI data sets. And So one thing we did try is actually training for much longer and seeing if that actually had an impact. So initially I wasn't just running hyperparameter optimization for 5 or 10 epochs, and I wasn't just running for 20 minutes. One thing we found is that performance generally tended to stabilize. So we weren't seeing significant improvements or significant changes in our results, even for like 30 minutes and so on. And because they tended to stabilize around this mark, then when collecting data for all of the data sets, because there were a lot of data sets and we wanted to do it within a reasonable number of days, I then shortened the time periods. But that is a great question. And yeah, that's definitely one of the things that we considered is that if over time different points in our hyperparameter search space would be preferred more.
All right, thank you.
Thank you. Any other questions?
So I would like to ask about the future work that you pointed out, evolving hyperparameters at the same time as you evolve the architecture. And that's, of course, what we've usually done. But did you have a chance to look at, in the way that you did it, first evolve the architecture, then do the hyperparameter search, whether different architectures actually work better with different hyperparameters? Whether you found differences? Because that would suggest that evolving them together might also work.
Right. So because of the way that, so the first thing was, right, basically there are three sort of general kinds of architectures that we tend to see. There are LSTMs and TCNs, which pretty much exclusively get used on recurrent problems. And then there are various evolved shapes of feed-forward networks. So one of the things I was wondering about but didn't have time to fully investigate is, as you said, if there was a correlation between the chosen hyperparameters and the perhaps like the width of the internal layers or the depth of the trained neural networks. But between LSTMs and TCNs, I did not see any kind of correlation with hyperparameters. They're just between those two models for recurrent problems. But yeah, the more general question, I have not investigated that. It would be interesting to look into.
Yeah. Yeah, I mean, part of this kind of studies is first you get something to work, and the second phase is to try to understand why it works.
Right, absolutely.
And then this kind of analysis looking at what did you find as architectures, what did you find as parameters, are there correlations? That's always interesting and could be insightful. Similarly, another interesting direction is, since you have these data set descriptions, meta level descriptions of what's in the data set, I'm wondering if that could be useful input also for the neural architecture search. So of course it gets feedback of fitness based on how well the architectures work, but also knowing what kind of data set is being evolved might be useful. Have you thought of doing something like that, incorporating that, and how could you incorporate it?
So, right, I think that's basically the question of meta learning, right? Is taking the data set meta features and using that to inform the architecture search problem. Not just, not even just tweaking the search space itself, but even just what kinds of models are you even going to try to train on the problem. I haven't gone too deep into that literature, so I'm hesitant to say anything much more beyond that. But it definitely would be an interesting to take this this in. My main concern is just that you need a lot of data sets to draw strong conclusions. And most data sets tend to be relatively easy to the extent where they can be solved with reasonable accuracy using not even neural networks, but just boosted decision trees and the like. And so it can be difficult to find enough data sets to draw a strong relationship between what kinds work and like what kinds of models you should be searching over for each one.
Yeah, I mean, again, it could help in explainability. I mean, if you were using those as inputs, you might get some regularity that certain kinds of architectures emerge with certain kind of meta inputs, and therefore be able to explain what architectures actually work. And that would be very interesting. It could be a tool for understanding as well as improving the mechanisms.
Right. One other general issue which I didn't actually mention is whenever you talk about having a distribution of data sets, you're always sort of subtly implying that there is sort of a population of data sets that you are sampling from. In other words, this is a representative sample of data sets. Like if you're going to put your model out into the real world, what is, you're sort of a Bayesian prior claim, right? What is the expected distribution of data sets you're going to see? And that can be a difficult claim to make, especially given how hard it already is to source data sets from different places. But if you put out a model for a while and then you get data sets from people, then maybe you can draw conclusions about those kinds of claims.
Okay, thanks.
Thank you.
Krishna, nice presentation. Thank you.
Thank you.
My question, I think, has some overlap with Anthony's, but here we go. You're dealing with a time budget here for your anytime algorithms.
Yes.
So if you take time to do a hyperparameter optimization, it's coming out of your overall budget.
Mm-hmm.
So that's less time that you could be spending on, say, neuroevolutionary search.
That is correct, yeah.
Feature extraction or other parts of the machine learning pipeline. Do you know whether that's time well spent in general? So your thesis is focusing on what kind of benefit is hyperparameter optimization providing for different kinds of data sets. And you found in general, it's not as big of a benefit as you might like. So where would that time be better spent?
That's a great question. So the initial idea for the thesis was to experiment with different ratios. So given a fixed time budget, to try different ratios between allocating X minutes to hyperparameter search versus X minutes to, as you said, to the actual architecture search. There were a few observations that caused me to change this. One is just that, this is very time consuming to run all of these experiments. Two is that we didn't see many significant improvements in performance on even the most difficult data sets past roughly 20 minutes, or even less than 20 minutes of the main architecture search. Darwin does actually have an internal detection mechanism for stagnation stopping, which is where it will, it'll run your neuroevolution, and then if it finds that it's not getting any better, it'll just stop early and tell you. And one idea was we could have started running our hyperparameter search once the stagnation stopping triggered, and then run it until the overall time budget is met. In general, you could probably imagine this as running for a total of 30 minutes and allocating 30, 25, or 20 minutes instead of the 20 minutes we did allocate to neuroevolution. And I personally conjecture that the results would look very similar, just because they didn't generally improve much beyond 20 minutes. But given 20 minutes, then at that point, then you have the question of, is it worth it to try hyperparameter optimization? And I would personally guess no, just because, again, you do want the better models, the LSTMs, the TCNs, to start beating out the weaker ones for those difficult problems. And that, in practice, does not generally happen with much shorter time limits.
Okay, thank you.
Thank you.
So thank you for your presentation. This is very much outside my field, so I can only ask kind of high-level questions. And the high-level question that always is important here is, what exactly was your contribution here? What, where did the ideas come from, et cetera? Can you just sort of, because, people tend to be humble and they don't tend to use the word, I did this, and then, beat themselves on the chest. And when it comes to these kinds of presentations, that's actually what we're here to judge, right?
Right.
So beat on your chest a bit here.
Okay. So this was, as I sort of mentioned at one point, this was my internship task, was to integrate hyperparameter optimization into this product, Darwin, and to draw as many conclusions as I could. And then this research is hopefully a little bit more general than that, but is still, in practice, it tends to be a bit specialized towards that problem. Now, I personally implemented hyperbanded random search. I implemented a more general interface inside Darwin to do hyperparameter search. I also did various other things which are not super relevant to this because that was just my general internship. But for relevant to this thesis, I programmed the algorithm and so on. I also wrote all the code for for using the library to extract meta features and do the data analysis, although I did not write the code that actually computes the meta features directly, as I used the library provided by Rivoli et al. I think that's basically my contribution. I don't think I did that much else relevant to this paper.
Thank you.
Thank you.
That's all for my questions. Should we dismiss the general audience and go into closed session?
That sounds good. Is this the Zoom equivalent of sending them out to the hallway?
Well, if we still have questions specifically ourselves where we would like to ask them without the general audience, the general audience needs to log out now, please.
Got it.
Okay, they're gone. I don't have any further questions. I get the impression that both of you have asked your questions as well, or Risto, you have anything else?
Yeah, I just quickly wanted to know the scope of Darwin, that Darwin helped you. Darwin has the way of doing a neural architecture search.
Mm-hmm.
It also has the way of training the neural networks and running experiments. So what your contribution really was to add a new plug-in component to Darwin, which was the hyperparameter optimization. Just wanted to
Well, I actually did make, so I actually forgot about this, but I did make some reasonable contributions to Darwin's testing framework because I needed to run these experiments I had a lot of experiments to run, and I wanted like partial logging, and I wanted certain other changes to their testing framework. But the bulk of it was already programmed before I had shown up.
Mm-hmm.
And the bulk of the data sets were already sourced by other engineers at Darwin. So I had not written that much code in that regard.
Yeah, that's fine. Just wanted to make it clear.
Yeah, Darwin also trains, so I think I mentioned this as well, Darwin also trains other kinds of models, not just neural networks. They use a Gaussian process to optimize random forests and XGBoost models. They also have ensembling techniques, which are programmed in so that they can take the best of both the neural networks and the sklearn models. I either disabled or ignored the results of both the ensembling methods and the non-neural network models. But I did train for long enough that the neural networks generally beat out their more primitive counterparts.
Okay, cool. I'm good.
All right. So usually it has been recommended that we now create a breakout room, but I have no idea how to do that.
All right, let me see if I can figure this out. I haven't done this before either, so let's see. First of all, let me stop sharing, right? Okay.
You need to put the three of us into a breakout room.
Ooh, that's new. Usually we just send the student.
Yeah, why don't you just
room.
step out and somebody will send you an email.
Sure. Let me make someone else a host just in case. I'm worried that the room will. Well, I think it'll stay even if I leave. So let me leave.
It does. Usually it does. Yeah.
So,
Okay, we do want to turn off recording